Yeah, yeah. I'll make a short introduction of Dr. Ozkan. Dr. Ozkan is professor of petroleum engineering at Colorado School of Mines. His areas of expertise are reservoir engineering, fluid flow in porous media, PTA, RTA in unconventional reservoirs. Dr. Ozkan is a distinguished member of SPE and recipient of different awards. He has served as a SPE Reservoir Technical Director, co-executive editor and chief editor of Journal Petroleum Science and Engineering. Dr. Ozkan has over 170 technical papers, one book, and several book chapters. And he is also a former SP Distinguished Lecturer in 2011-2012. And what I want to say that today we are not having just a webinar, so it's distinguished lecture. It's one of the most interesting presentations that was selected by SPE International to present to the members of local sections and chapters. So Dr. Eskan, the floor is yours. It's immense pleasure and honor for us to have you here today with us.
Thank you very much. It's a pleasure for me to, at least virtually, present this talk. And Distinguished Lecturer Program is one of the flagships of the Society of Petroleum Engineers. As you know, one of the main missions or objectives of SPE is to disseminate knowledge. And to do this, SPE has journals, one Petro library, and this SPE Distinguished Lecturer Program. And through this program, we try to share and distribute knowledge. And at the same time, conversations and discussions actually cross-fertilize some of the opportunities worldwide. So we are thankful for the primary funding provided by the SPE Foundation through their member donations and also a contribution from offshore Europe to make this distinguished lecturer program possible. And also, of course, me and other distinguished lecturers are supported and allowed by their companies, their affiliations, to make these presentations, to spend the time, travel, and everything else. So we are grateful to those companies. There is also additional support from the AIME, which is the umbrella organization of SPE. So with that one, I would like to start my presentation, which is, as Yuri mentioned, one of the most popular, one of the most interesting topics these days. It's CO2 EOR and sequestration. And here I also add a subtitle. I mentioned challenges on Pore scale. And during this presentation, I will try to make it clear why I look at the challenges on Pore scale also. Just to guide your expectations during this talk, I will just mention a few takeaways of this talk. First of all, we should understand that storage in geologic reservoirs is the best option to sequester CO2. So that's why this is a hot topic. Second, I will just emphasize that unconventional reservoirs will be a good option for CO2 sequestration. But at the same time, CO2 sequestration is not an inexpensive process. There is a cost associated with it, and to help offset or balance the cost, CO2 sequestration may be combined with enhanced oil recovery, and this is what we are going to consider today. Another topic I will use or I will emphasize in this presentation is that the physics of CO2 sequestration and the physics of enhanced oil recovery are not necessarily the same. So there will be some conflicts, and we are going to talk about how to optimize them. And finally, because we are going to mention some unconventional reservoirs where the pore sizes are extremely small, we are going to mention the importance of pore scale phenomena for CO2 EOR plus sequestration. Now, the outline of my talk will be in two parts. In part one, I will talk about physics and efficiency of the processes. This is more of a general presentation, but in part two, we'll go a little bit more into the technicalities, and we are going to discuss some of those pore scale and molecular level challenges. So let's start with the physics and efficiency. Based on the USGS methodology to assess CO2 storage potential, we can consider two types of CO2 trapping mechanisms. One of them is called buoyant trapping. The other one is residual trapping. As you can see on the right-hand side, the buoyant trapping is basically CO2 filling up the pore space between sand grains or the mineral grains. And in this case, you're basically using a void volume as storage space, and then you're trying to seal this volume by impermeable top, bottom, and lateral seals. So this is more like our conventional trapping mechanisms. And on the figure on the left-hand side, you can see that the buoyant trapping is mostly associated with structural traps, just like in our conventional reservoir systems. Residual trapping, on the other hand, is due to the surface tension and the surface forces basically keeping CO2 stuck on the surface of the mineral grains. And in this case, instead of relying on some type of lateral and top and bottom seals, some sealing formation, you mostly rely on the physics of the system, surface forces, absorption, all this type of phenomena. And because of that, this type of trapping is more active in basically unconventional type of reservoirs. As you can see here, this is very low permeability medium, but at the same time, it has a lot of storage opportunity because these are basin scale accumulations. So compared to buoyant trapping, residual trapping may offer a much larger potential volume. And on top of this, because it does not require some type of sealing mechanism, some type of sealing formation on top of the structure, it may be more reliable. Remember that when you look at the seal, most of the time the seal is shale. And today we are actually producing from shale. So shale is not necessarily completely sealing formation, but depending on the conditions, it may act like a seal or semi-permeable barrier. So it's not certain that the CO2 will stay in this structure. So this is one of the problems. But I'm going to look at this issue a little bit more in the next slide or so. So when we look at these two trapping mechanisms, buoyant trapping is mostly at the top here of the triangle, and the residual trapping storage resource, it's at the bottom, which is more in terms of volume. But this is not just about the volume. It is about also the mechanism of trapping. And there are some other issues. If you are going to inject CO2 into the reservoir, then you will be concerned about the injectivity issues and also the time scale. As I mentioned, if you are relying on some sealing formations, you should make sure that in a reasonable time scale, this CO2 will be securely trapped under the ground. So from that perspective, I made a classification here. If you look at high permeability, more conventional type of reservoirs, you're relying mostly on buoyant type of trapping, because this type of traps are usually structural traps geologically. We're talking about relatively small storage volume. Yes, when we look at the magnitude of the volume, it may look high, but at the same time, when you consider the amount of CO2 emissions, how much CO2 we need to store at the end of the day, these conventional type of structures will not be sufficient to get rid of the large CO2 emissions which we are trying to get rid of these days. If you are talking about higher permeability formations, of course, there are no injectivity problems here, but the time scale to keep this CO2 in the storage is shorter. So because of this relatively small storage volume and short time scale, we can consider this type of storage as low storage efficiency systems. Medium permeability storage, on the other hand, is mostly tight conventional type of reservoirs. And here you have a combination of both buoyant and residual trapping. The volume is still relatively small. Here, you have still reasonable injectivity, and time scale to keep the stored CO2 in the system may be medium. So you can talk about good to low storage efficiency. The last one is low permeability reservoirs, much smaller than 1 millidarcy permeability, which is unconventional type of reservoirs. Here, you rely on residual trapping, and there is abundant storage volume because unconventional reservoirs are basin scale structures or independent of the structure, actually. It's a basin scale system. However, because of their low permeability, you may consider some injectivity issues, but at the same time, the low permeability property of these systems, the time scale is long. Therefore, there is medium to low storage efficiency in these cases. Because I mentioned this time scale issue, let me try to expand on this a little bit. So here on the left-hand side, we are looking at the time to move fluid 1 kilometer in an ordinary reservoir. Here, I just picked up some numbers. For example, the distance we are considering here is about 1 kilometer to move the fluid. And then porosity is 5%. You have compressibility and viscosity of the fluid here. And what I'm using here is nothing but the radius of influence formula. So basically, I use the properties of this formation to find out how much time it takes to move the fluid 1 kilometer. So if you look at the permeability values in the range of 1 Darcy, which have excellent injectivity and everything else, but in 1 Darcy type of formation, your fluid will move 1 kilometer in about tens of days, which means extremely fast. Under these conditions, it will be very difficult to contain the injected CO2 in the reservoir It's very mobile, and sealing the formation is going to be an issue. If you go down to 1 millidarcy range, then you're talking about hundreds of years, provided that your seal stays intact. But when you go down to 1 nanodarcy type of formations, these are unconventionals. Now you're talking about hundreds of million years. This is more like geologic scale. And that's why I was saying that unconventional or tight reservoirs, nanodarcy permeability reservoirs, provide a very safe medium if you consider CO2 sequestration. So we are going to look at some of these issues related to unconventional reservoirs. But before going there, we need to look at another issue, which is one of the problems we need to solve, or we need to understand if we are going to use CO2, EOR, and sequestration together. First, we need to understand that for EOR applications, if your CO2 is trapped in the formation, that's a loss. But for carbon capture and utilization, it is called associated storage. What I mean by this is if you consider CO2 for EOR, then you want your CO2 to mix with the oil, and the more CO2 mixes with oil, the more miscible the system gets, the better the oil recovery. But that means your CO2 will move with oil and come back from the other side from the production well. So most of the time, what we want to do is to separate CO2 and re-inject it into the formation, because CO2 is an extra cost for EOR operations. But also in this case, if your CO2 comes out from the other side, that means if it is not retained in the formation, then there is no sequestration. The objective of CO2 sequestration is to retain more CO2 in the reservoir. As you can see, the objectives of EOR and sequestration are in contradiction in this sense. So when we talk about efficiency, we need to use some quantification measures. For this, we normally use CO2 utilization ratio when we look at the EOR. In this case, the volume of injected CO2 per incremental barrel of oil produced is called the CO2 utilization ratio. As explained before, you can understand that a better CO2 EOR operation should use less CO2 to produce more oil. Therefore, your utilization ratio should be low to mention that your EOR process has high efficiency. On the other hand, the retention capacity is more related to sequestration. In this case, the difference between injected and recovered CO2, which means the retained CO2 volume in the reservoir with respect to the injected volume, this is your retention capacity. So when your retention capacity is high, that means you have sequestered more CO2 in the reservoir. There is one other concept you may come across. It's called net utilization ratio, which is the product of utilization ratio and retention capacity, which is basically retained volume of CO2 per incremental barrel of oil produced. So how do we use these measures? Let me show you some some application here. In this case, we are looking at a light oil carbonate reservoir. And this reservoir actually, even though I don't provide the details, this is an actual reservoir in the Middle East. And it's a deep carbonate reservoir. And it has light oil. we modeled the reservoir and we ran some scenarios to look at the EOR and sequestration efficiencies in terms of utilization ratio and retention capacity as a function of residual oil saturation, aqueous solubility of CO2, injected pore volume of CO2, and water alternating gas ratio. Now here, I just qualitatively summarized these results. As you can see, if you just look at the residual oil saturation, when your residual oil saturation increases, your EOR efficiency increases, but your sequestration efficiency decreases. As your aqueous solubility of CO2 increases, your EOR efficiency increases slightly, but sequestration efficiency decreases. Injected pore volume of CO2, how much CO2 you inject. If it increases, then EOR efficiency decreases, but the sequestration efficiency also decreases. And if you look at the WAG ratio, both your EOR efficiency increases, but your WAG ratio does not affect your sequestration efficiency significantly. So you can see that there is a mixed bag here. Your EOR efficiency and sequestration efficiency has different reactions to some of the key design parameters of EOR and sequestration. When we look at this in terms of unconventional reservoirs, we have also some interesting results. For example, on the Eagle Ford formation, they looked at a 12-cycle CO2 half and puff operation over 8.5 years. This led to about 62% additional recovery, but only approximately 13% of CO2 retention. So it is not really significant, as sometimes we try to believe that CO2 retention through EOR applications would get rid of most of the CO2 emissions. Another example is in the Bakken field, and here, based on conventional EOR experience, I should underline this, they estimated about 26% CO2 retention, and again, it's not as high as we would like to have. I also went ahead and I found some references in the literature and did the math and tried to get some averages for conventional and unconventional projects. As you can see here, for conventional CO2 flood and water alternating gas EOR applications, gross utilization ratio was 9.2. For unconventionals, it was 27.4. Remember, utilization ratio must be low for EOR efficiency to be called high. Therefore, conventional reservoirs have a better EOR efficiency compared to unconventionals. And then when you look at the retention capacities, your conventional systems will have about 48% retention capacity, whereas unconventionals will have 33% retention capacity. So for these numbers, you can say that for 1 barrel of unconventional EOR oil, you need to use twice as much CO2 with respect to conventional reservoirs. So this indicates lower EOR efficiency. And 15% less CO2 stored in the reservoir, again, based on retention capacity comparisons. So lower sequestration efficiency is seen also. However, EOR and sequestration efficiencies may be low in unconventional reservoirs, but For 1 barrel of unconventional EOR oil, you use 170% more CO2 to be sequestered. Now, these numbers are a little bit confusing from which perspective you look at it. You can just look at the face value of these numbers and say that unconventional reservoirs are not good for the CO2 sequestration through EOR. But at the same time, when you look at the produced volumes of EOR oil, in these cases, you sequester more CO2 in unconventional reservoirs. So this is one of the recent problems. We use statistics a lot these days. We use data analytics, artificial intelligence, and everything based on the face values of these numbers. But from this table, if you want to say that the CO2 sequestration is not good in unconventional reservoirs, you can use the top half of the slide. But if you want to also defend that CO2 sequestration is good in unconventional reservoirs, you use this last line. So it's just your choice. Pick up whatever you want to support, and there is always data to support it. But we are engineers and scientists, so instead of just supporting an idea based on just some pure numbers, we would like to look at the physics of the processes and understand what is really happening. One of those measures is actually called exergetic efficiency. So exergy is basically a measure of the work done to conduct a process. And here, when we look at the exergy recovery factor, we can just say that the difference between exergy gain minus exergy invested scaled by the available exergy in the reservoir is going to be your exergy recovery factor. Now, CO2 source here is a key variable. Normally, if you just look at the case with captured CO2 and use this captured CO2 for EOR purposes, you need the 7.7 M standard cubic feet of extra CO2 per barrel of oil. And in this case, you have about 30 to 40% less exergy than the process with natural or produced CO2 from any underground resource, for example. So based on that, we can also say that EOR with captured CO2 may not be sustainable. Why are we saying this? Because there is a high exergetic cost of CO2 separation from flue gas currently, and additional carbon emission in capture processes is still high. So this is not an issue with the storage under the ground. This is a problem with the capture side of CO2 operations. So we need to understand that today there are a lot of subsidies for capture processes and even to incentivize some of these storage opportunities. But at the end of the day, this is an economic process, and the nations will have to spend their wealth for a lot of different things. They cannot keep supporting CO2 sequestration forever. At some point, this process has to be self-sufficient, sustainable by itself. And today, we are not at this point. And to come closer to that point, we need to improve CO2 capture processes, and also carbon emissions from capture processes should be reduced. So with that one, I would like to move a little bit more into the technical topics. And here, I'm going to look at the pore scale concentrations, because I mentioned that some of those unconventional reservoirs with very small pore sizes, but extremely large bulk volumes may be good options for CO2 sequestration. One of these concepts we need to understand here is filtration through small pore spaces. Shale is known to have membrane properties, and this was discovered by exploration geologists in the last century, about almost like 80 years ago. And also, when you look at the light oil production from unconventional reservoirs, you realize that under the ground, you do not have for the API gravity oil. Probably going through these very small pore spaces, some of these heavier hydrocarbons are filtered. That's the reason why we only produce or why we only get lighter hydrocarbons at the surface. So to test this idea, we ran some experiments at our lab, and we used a mixture of C10 and C17, and we moved this through conventional Berea sandstone. And here, what you see is C10 pore volume, C10 percentage composition, and as a function of pore volume injected. The black dot here is the injected C10 concentration, and the orange data points are the C10 concentration produced from the other end of the core. As you can see, when the injection continues, there is almost no difference between the injected and produced C10 concentration. That means C10 and C17 concentrations do not change. There is no filtration. When we repeated the same experiment with the Niobrara pores, here your pore sizes are at the range of nanometer size, and here your injected C10 concentration is the blue dot, but produced C10 concentration denoted by the orange data point is much higher. So when we look at this figure, we understand that if the C10 concentration, produced C10 concentration is higher, that means C17 is filtered and it's not passing through this pore space. Just to see the effect of CO2, we stopped this injection at some point, and we injected CO2 from the injection, from the production end into the core, and we waited for a while. So this is more like a huff and puff process. And we opened the injection end again, and we looked at the effluent fluid concentration. Now you can see that your C10 concentration goes down significantly after a soaking period. That means you produce more C17 after the soaking period. Heavier hydrocarbons start flowing in the system until at some point this CO2 effect is lost. So you go back to the same level. At this point, you basically shut down the system, inject CO2 again, soak it. But what this tells us that CO2 injection, CO2 soaking may increase production of heavier hydrocarbons. So this is the basis of CO2 EOR in unconventional reservoirs. It reduces the filtration effect and it helps production. To understand it a little bit better, you can just look at these two pictures on the left. The first picture on the left is a commercial depth filter used in the industry. And the one on the right is a mudstone, which is shale, basically. You can see that the pore structures are quite similar to each other. So in these types of systems, your molecular structures may not be suitable to pass through these pore openings, and some of them get trapped because of size exclusion molecular sieving, molecular dispersion, crowding effect, selective diffusivity, and selective absorption. So we used some of the theory available in the literature, and we also adapted some of our original oil technology concepts. And we started modeling this in a representative pore system here. As you can see, we have some larger pores, some smaller pores, small pore throats, and different size hydrocarbon molecules will have to pass through the system. Now, if you had much larger pore spaces, then there would not be any issue for this entire composition to pass through. And as we saw in the Berea sandstone, we would see more of a bulk transport. Compositional changes will not be significant. But here, as you can see, some of these larger molecules may be limited in passing through these narrow channels. So only some of them will end up in the second and maybe not in the third pore. And depending on the mobilities of these smaller pores, by the time you move the fluid through this pore system, you will experience some compositional change. And some of these changes will be because of pore sizes. Some of them will be because of surface forces. So we have some advective diffusive transport system here, and the preferential adsorption, molecular sieving, and anomalous transport will cause what we call a hindered transport system. So to be able to model these types of systems, you need to look at molecular pore scale physics. You need to do some compositional modeling, and you need some new phenomenological definitions and their quantification. Just to explain slightly more, I don't want to go into the details of the system, but this is our standard continuity equation. Influx, outflux, difference is the accumulation. And when we look at the outcome of this modeling, we have the flux terms on the left, and these flux terms, the difference between the flux terms should be equal to the accumulation in the pore system. So we have first the pore volume accumulation. We have accumulation due to absorption on the pore surface, and we also have some sieving mechanisms, as I mentioned before. So far, this may seem to be slightly conventional. We incorporate some absorption properties in our modeling. Sieving, we do not really deal with in conventional modeling. We need to look at that. But more importantly, when you have absorption and sieving, some of those dispersive and advective flux terms will also go through some changes. And our conventional flux terms, unfortunately, do not handle these types of influences. Therefore, they need to be modified. So let me tell you what I mean. For example, we talked about diffusion, and here on the right-hand side, I will show you a simulation here. In these tubes, there are two lobes, and they are connected by some, let's say, pore throat. And in the left-hand side here, we have two molecules, methane and heptane. And methane is the smaller molecule with more mobility. And let's see what happens. Now you can see that they have these agitations, they move, and methane being smaller, it made so many moves and eventually found this space through the opening, the mouth of the left lobe, and moved into the right side. And now it's coming back, and eventually the larger molecule heptane wants to go out, but at this time it gets stuck because it cannot really pass through this opening here. So what we demonstrated here is the fact that smaller molecules can move more frequently and make larger jumps. For example, if you look at helium, methane, and oxygen, helium being the smallest molecule among all, you can see that it makes much larger jumps in the same time frame, and it can make more moves. Therefore, as I demonstrated in this simulation here, it can have more opportunities to move through the pore space. And as a result, different size molecules may have different diffusion characteristics, and the characteristics of porous medium, meaning that the pore and pore throat sizes may also change diffusion characteristics. For example, we did some molecular dynamic simulations, and as you can see here, the diffusivity of methane is much larger than the diffusivity of butane and also octane, hexadecane, and pentacosane. Therefore, methane is 5 times faster than butane and 25 times faster than pentacosane. As a result, when you look at the produced fluids, natural gas or oil, through these unconventional systems, you see more lighter components than the heavier components. Also, depending on what type of mixture this component is in, would also affect its diffusivity. For example, here, we consider niobrara oil, and we look at, for example, hexadecane in niobrara oil in brown, hexadecane in niobrara oil plus CO2 in blue, and hexadecane in niobrara oil plus methane. Here we just wanted to look at produced gas injection also. And you can see that the diffusivity of hexadecane is different with respect to, excuse me, to these 3 scenarios. And for example, for butane, there is a huge difference when you add the CO2 into the mixture. But for pentacosane, it doesn't make much difference. So what this picture teaches us here is that normally when you do some compositional simulation with some diffusion in the model, you pick up some diffusion coefficients from the literature. If you go to your classical chemistry books, you normally see just one number for the diffusivity of methane, ethane, you name it. But here we can see that there is not just one single diffusivity coefficient. Depending on what's included in the fluid mixture, the diffusivity coefficient will have to be recalculated, readjusted. Another interesting finding from molecular dynamic simulations is shown here. And in this case, we used 2 calcite walls here, and this is a 10 nanometer pore opening, and calcite faces represent carbonate surfaces here. Initially, we filled up this space with niobrara oil molecules here. And as you can see, most of the molecules get stuck on the surface of the pore space. When we start injecting CO2 molecules into the system, which are denoted by these red dots here, because CO2 has more affinity to calcite, CO2 wants to stick or adsorb on the calcite surface. To be able to do this, it starts stripping some of the oil molecules from the calcite surface. The more CO2 injected, the more hydrocarbons are pushed into the middle of the pore space, and eventually all these calcite surfaces, all these adsorption sites are occupied by CO2, So additional CO2 starts swelling the oil in the middle, and it reduces the viscosity, and its mobility is increased. Therefore, you get more production. So this is different from conventional CO2 displacement. There is also an added component of adsorption, and adsorption actually improves the production of oil because of oil stripping from the surfaces. In fact, when we looked at this in terms of surface storage over bulk storage, here you can see that when the pore space opening becomes smaller, your surface storage becomes much more than the volume stored inside or the bulk volume. That brings us back to the original storage phenomena I showed you. If you look at the buoyant storage mechanisms, that means filling up the pore volume. If your pore volume is small, then most of the storage is based on surface holding, retention. So that's more active in unconventional reservoirs. Also, you can see here that the adsorbed CO2 dominates storage in low bulk density. So that also indicates that in low or small pore sizes, you rely on adsorption density or adsorption phenomena more than just the bulk volume. And one more interesting feature I would like to show before going to the conclusions is that we normally think that when the adsorption on the pore surface increases, the permeability, effective permeability decreases because you're narrowing the channel, which is true up to some point. But as you can see here, if the pore opening is small, for example, 8 nanometers here, after you reach some critical adsorption density, actually this adsorbed molecules will help your permeability. It will increase your permeability by up to 20%. So the reason for that is the slip effect introduced by this adsorption volume, and this causes some type of diffuse osmosis phenomenon here, and diffuse osmosis enhances flow by about 35% if the pore opening is 10 nanometer, and up to 98% if the pore size is 6 nanometer or less. So there are a lot of interesting features if you want to understand what's going to happen when you inject CO2 into these smaller pores, because CO2 in these small pores combined with the existing hydrocarbon molecules will have an interesting physical interaction, which is not usually considered in our conventional modeling. So key considerations here will be like, first of all, to be on the positive side, there is definitely a promise for CO2 EOR and sequestration, and the medium to low permeability reservoirs may be a good option. However, we need to understand the contradicting objectives of EOR and sequestration and their different physical mechanisms. CO2 EOR plus sequestration is a challenging optimization problem between oil recovery and CO2 retention. When pore sizes shrink, then you need to look at the pore scale or molecular scale effects, and you need to rely on diffusive mechanisms because they dominate the transport. So in the end, more work, more understanding is needed to establish new relations and new data to model this type of phenomena. So the bottom line is for CO2 EOR to become an economically and technically viable solution for sequestration, first of all, carbon capture technologies should be improved so that the economics would be favorable. Exergetic efficiency must be improved, all in all, and we need to understand better the pore-scale mechanisms to be able to effectively model CO2 EOR and sequestration processes. So with that one, I would like to conclude my presentation. Your feedback is always important, and I encourage you to enter your section in the DL evaluation contest by completing the form in this website. And now I'm open for your questions. Thank you.
Yeah, Dr. Ozkan, thank you very much for a great presentation. It was not so easy as we expected in regards of reservoir, but it's another challenge also like about like surface, just to like select the proper materials like that are not so I would say affordable to us, to build infrastructure with compressors like pipes, flow lines, wells, casing, tubing, and so on. Yeah, but thank you very much for describing into details the challenges that we can face in the reservoir. Yeah, I would like to ask one question. Can we apply for carbon credits if we are sequestrate the CO2 into the for EOR purpose?
Yes, in fact, this was one of the incentives the companies wanted to use. But even with the carbon credit, it's becoming more and more difficult to justify this CO2 sequestration. I can explain why this is the problem. In our unconventional reservoirs in the United States, some companies started using this carbon credit and government incentives in general to use CO2 for the EOR. And they actually reported up to 60% increase in their recoveries. So it was a good thing with all this additional benefits obtained from government incentives. But eventually, it started going down to 40% or so. And then they started looking at it from a different perspective. They made a comparison. They looked at how much money they spend and how much money they make out of this CO2 EOR plus sequestration process versus if they invest this money to explore some new reservoirs, new unconventional reservoirs from the beginning, they found out that their discoveries through exploration will give them better profit. So this concept is known as value of, time value of money, right? And also it's known as opportunity cost. So if you just look at whether it's profitable or not, yes, it may be profitable. But as long as you can spend your money to make more profit somewhere else, industry will go through this route. So that's what's happening in the United States. The difference is in Europe, there are some strict regulations. European countries, they do not want to produce any oil. They just want to get rid of CO2 and everything. So it's a different mindset. But that's why I mentioned if you want to make it long term, at some point, even European companies will not be able to subsidize all this cost. So there has to be some cost reduction. That's why we need to work from both sides, both the capturing side and also making it more efficient under the ground.
Got you. Thank you. Maybe some question from the audience. We have seen some applause, but maybe there are some questions. Yaroslav, Mykola, maybe some questions from your side.
Thank you. Not yet. Maybe my colleague. Thank you for your time, for very interesting introducing. It's very interesting for us, for our company, for Ukernafta, because we have a lot of old field, and EOR, it's one of methods what we want to introduce in our future.
As I said,
yeah,
go ahead, please.
Yeah, it's the biggest oil company in Ukraine, and Yaroslav Mykola is working for that company, and they're considering like CO2 as one of the ways for EOR.
And definitely it's gonna come. Its time will come. I was less than 3 weeks ago, I was in, for example, United Arab Emirates, and they have a lot of good fields, a lot of good production, but some of their biggest projects are CO2 EOR and sequestration. Everybody is trying to learn how to manage these projects. One of the issues we need to understand is that when CO2 sequestration, even hydrogen storage, some of these concepts come up, people think that, oh, if it's underground storage, this is our area. We can do that. We have been producing oil, so we can store everything under the ground. It is not that simple. Probably we are the closest to this problem, closer than anybody else, but at the same time, there is a lot of background we need to build. So before we can apply those successfully, we need to do our homework, we need to learn, and then when the time comes, we will be ready to execute in the field.
Thank you very much. It was very interesting. For our company, I think it is economic is on the first place, as it was in USA, of course. But this technology is our future, I think, and we will improve our knowledge about that. Thank you.
Thank you very much.
Hello, my name is Vitaly, and I also want to say thank you for this presentation. Actually, we were working a little bit with this technology of CO2, and actually our company wanted to implement this method. Now it's not possible because of the war, and it's really hard to find and to resolve the problem how to capture the CO2 from our plant. So, but in general, I want to ask you about like general question. How do you assess the impact of long-term storage of CO2 in underground reservoirs or on geological structures? I mean, is there any scientific evidence on the potential risk of CO2 leakage through microcracks? I mean, migration or something. Thank you.
Thank you very much. This is definitely an important issue. Right now, there is so much expectations around CO2 storage and from our underground reservoirs. But in reality, we know that if something escapes the storage medium, this causes a disaster and the blame comes on us. And for example, methane leakage, it happens. And CO2 is also a relatively small molecule, and it can escape some of those underground structures. And no underground structure, especially oil and gas reservoirs, and more so for salt salt caverns and some of those old aquifers. They are not completely sealed. So there is a potential. That's why I looked at the time scale. If there is some small leak from these formations in time, that can definitely find its way to surface. And this means that our storage efficiency is not good enough. But when people look at these things, they say that if oil and gas stays under the ground, then CO2 can stay too. No, it's not that simple. CO2 has different chemistry under the ground, and as a result, it can create some new cracks. It can actually go through the seal. So we need to understand these mechanisms better. That was one of the reasons I wanted to emphasize that unconventional reservoirs may offer a safer option because you don't need a seal. Here, the seal is more permanent because CO2 sticks on the surface of the minerals of the shale surface. So there are a lot of different options. We need to do the work. We need to understand what's going on. Right now, what people do, they just look at some pore volume and they say that if there is that much pore volume, then I can store this much CO2. No, this is not true because some of this CO2 will come out from the cracks from the existing wells or will just find its way through the formations over some 100 or 200 years. But we cannot just say that in 200 years, we don't care what happens. We have to make sure that it is going to stay there. So right now, to answer your question, I don't think we have a sure way of saying that CO2 can stay under the ground unless we can build all these models and we can understand how CO2 behaves in our underground reservoirs.
Thank you very much for your answering. And also about equipment, I have an additional question about equipment. Yuri mentioned about that we have to build new infrastructures for implementing and build new pipelines for delivering, right? And from your perspective or from your experience, can we use our old infrastructure, our old wells to sequences the CO2? I don't speak about maybe EOR, but for storage, maybe we can use all our maybe old wells that is not work now, and we can use them just for the storage. Or is it possible? Do we have any experience from any history from the history that maybe some company implemented this?
Yeah.
Yes. Go ahead.
Please, Dr. Ozkan, let me add to Vitaly's comment. And what is the best approach, to drill a new well or maybe to repurpose like an old well with like some additional casing from fiberglass, or just what is the best approach here? Thank you.
Well, all these issues you raised are definitely relevant. First of all, in terms of pipeline transportation, there is not much of an issue. We can usually use existing surface pipelines to transport either from capturing sites or industrial emissions to the storage sites. So pipeline is okay. The other thing is, of course, you need to invest on compression systems, and that's a big issue. And depending on how deep your formations are and what type of injectivity issues you face, this is going to determine your compression needs. And it's actually a huge investment. And you need to realize that when you inject CO2 under the ground, there are a lot of chemical reactions, especially when CO2 reacts with the formation water. You get a lot of mineral precipitation, and this blocks some of your pore channels, and it causes a lot of injectivity issues. Therefore, when your injectivity gets reduced, then you need to use more compression power. So that's another issue. In terms of the use of older wellbore infrastructure, there are always problems here because some of those depleted or deserted oil wells, they may not have good casing structures. Their cement may not be intact, and CO2 with cement, CO2 with formation water, and CO2, its corrosive effects on the metal may cause some issues. So, yes, there is definitely a potential. And I can say that these are not prohibitively big problems, but you should definitely check all your existing surface and wellbore systems to make sure that they are compatible with the CO2 chemically and also pressure-wise. And then the last thing is the reservoir side. When you look at the reservoir, you need to have two things. One of them is the seal. And the seal is maybe intact today, but when you inject CO2, of course, you're going to repressurize the formation, and you're going to change your geomechanical properties of the field. Stress field is going to be shifted, and this may create some new fractures. This may create some new cracks on the seal. So you need to do a good geomechanical study to ensure that you're not going to crack the formation or create some leakage through the seal. And finally, you need to have some good reservoir model to understand that your injected CO2 will be able to go deep enough into the reservoir, but not too deep to reach beyond the limits of your intended reservoir and find a way through under the ground to come to some water formations or through some cracks coming through the surface. So it's a high potential, and there are some applications of those both in Europe and in the United States. But if you look at the scale of CO2 sequestered through these projects, it's still quite minor, but there are definitely potential applications here, and it's promising.
One question. Can EOR exist without CCUS?
Yes, if you mean through natural CO2 by using some CO2 production from CO2 reservoirs. So far, this is mostly the application. CO2 EOR is the most common EOR technique in the world. And I must tell you that so far, together with some steam injection, CO2 EOR is the most successful EOR technology. You may hear about other chemical techniques like surfactant and everything else, but they do not actually produce much commercial oil. But CO2 EOR does. And in most of these projects, the injected CO2 comes from some other CO2 reservoir. And in the United States, the companies who consider CO2 injection for EOR, they usually have some CO2 fields, and or they have a deal with some company to buy some natural CO2, which is much cheaper than capturing CO2 through some processes.
Okay, thank you. And the last question, I want to touch the topic about delivery. So we were talking with different companies from Canada and from Norway, and like different discussion, different point of view about how to deliver the CO2 into the well. And some of them is considering that it's better to, like, not better, but maybe from the beginning of the project, it's better to deliver it by the truck. But I have here some problems and some issues because of the local people and how to, because you need to like continuously deliver it by the truck. But others said that like it's not good idea. It's better to build a pipeline, but it's a big investment for that. So what is your opinion about that?
Well, I think at least theoretically, using transportation by tracks will be okay. And in fact, I was just looking at a project recently, and they had similar concerns. But I would like to look at it this way. If you are going to build an EOR project, the approach for that, first you'll do your lab tests, you do your simulations, and then you move into some kind of pilot testing. That means you use either one well or a few wells to test the process. So at this point, you may not want to invest into building a pipeline. So during this time, you can use trucks to bring CO2 just for this limited scale CO2 EOR operation. But if it proves to be good, and if you want to continue the project in field scale, then carrying CO2 by trucks will not be sufficient. There is one exception to that. If it's a small field, and if you are going to use CO2 mostly for pressure maintenance to some degree, then maybe some small volumes of CO2 can be transported by trucks. But in general, if you are going to go to a mid to large scale field operation, eventually you will have to build some pipeline. But as I said, I would probably not build the pipeline from the beginning until I make sure that the pilot operation proves to be successful.
Yeah, the same opinion. Okay, thank you very much.
You're welcome.
Okay, any more questions? Okay, if there are no questions, Dr. Ozkan, please accept from our side great appreciation of your time and willingness to explain us the topic, which we think will be part of our future soon. Yeah, but we are already talking about that. And also, I would like to thank you to our admin chairperson, Katerina Kategra, also for making the registration event and and all the support with that event. Yeah, and we do hope that in the nearest future we'll be more ready with our R&D project for CO2 sequestration, or for CCUS, or for EOR. and within the nearest future, you will come to Ukraine with some like a business trip, like to help us boost our projects.
I appreciate this. In fact, I was in Ukraine, I don't know, maybe some 8 years ago, 6 to 8 years ago, and it's a beautiful country, and I would love to come back and maybe have these communications face to face in not so distant future. But for now, I thank you for the invitation, and I wish you the best of luck with your projects. Thank you.
Yeah, thank you. Thank you to all the participants, as well as we do appreciate that you joined us and it was interesting to you. We'll be organizing like more events in order to satisfy the needs of our SPE members locally. Thank you.
Thank you for this
Okay.
interesting event.
Thank you.
Bye.
Thank you.
Thank you.
Thank you very much.